Hello, I'm Anthony Pepitone, and this is Lab 4, Oscillations. In this lab, we will be looking at the purpose, fundamental ideas, initial conditions, as well as a video and a model to figure out how oscillation works. The purpose of this lab is to observe the motion of a mass that is swinging in 2 dimensions. From this, we can create a computational model to predict the object's motion and energy changes. Along with this, we will observe and understand how this applies to the energy principle. As a result, we will see the total change in energy of the system is 0, which satisfies the energy principle. The main topic of this lab is the energy principle, which states that the change in energy is equal to the work of the surroundings. There is no work being added or taken from this system, so there will be no change in energy. Along with this, we'll be using Newton's second law, the velocity and position updates, to code the model, and we'll be using the spring force equations to code the spring throughout the lab. For the initial mass, we have 0.402 kilograms. Along with this, we have the initial position of negative 0.101, and in the y direction, negative 0.640. Along with this, we have the length of 0.7 meters, no initial velocity, and our system is going to be the Earth, the mass, and the spring. Our surroundings for this is going to be everything else, which we will see has no work. This is the experimental video, which was tracked by Tracker to find the movement and oscillation of the mass. As we can see, the mass moves in both the x and y directions, making it a two-dimensional movement. On the right-hand side, we can see the calculations that allow us to find the spring constant and L naught. For the first part of the code, we're going to take the initial conditions. This is that the ball's mass is 0.402, the initial position which we looked at earlier, and the velocity. On the right-hand side, we take our constants and other things that need to be defined. This is the gravity, which is 9.8, the spring constant of 6.83, and L naught, which is 0.123, which we calculated earlier. Along with this, we're going to be taking L and L hat along with S. Finally, we are going to be taking the kinetic energy, 0.5 times the ball's mass times the velocity squared, along with the potential energy of gravity, which is the ball's mass times gravity times the ball position in the y direction, and the spring potential energy, which is 0.5 times Ks times S squared. Lastly, we're going to be using the energy, which is all of these things added up. For the next part of this code is going to be the calculations, which we'll be taking at each timestamp. First, we have the force of gravity and the force of the spring, which we talked about earlier. Along with this, we have L, which is the ball's position minus the spring's position, L hat, which is L over the magnitude of L, and this S, which is the distance of the spring, which is the magnitude of L minus L hat. Along with this, we're going to be calculating the energy for each step, which is the same equations we used before of 0.5 times ball's mass times the ball velocity squared, the potential energy for gravity, which is the ball's mass times gravity times the ball position in the y, and the potential energy of the spring, which is 0.5 times Ks times S squared. When looking at the data and the graphs from the model and the experiment, we can see that they are pretty close but not exact, and this could be due to a couple errors. First is that there could be other forces acting on the mass, such as drag and air resistance. These are not calculated since we are taking only the mass of the object, the spring, and the earth as the factors. Along with this, when choosing the center of mass for Tracker, there could have been some errors in choosing the exact center of mass. Finally, there could be errors in the oscillation period in the y direction, just from errors in calculation. When looking at to see if the energy principle is satisfied, we can agree that it is. This is because if you look at the yellow line on the graph, we can see that it is staying at 0. Because there is no outside forces, it shows that there is no energy being put in or put out. Therefore, the change in energy is 0. Lastly, we could look at the oscillation periods for the x and the y direction. This is done by taking the distance between the two peaks and the time it takes to reach them. For the x direction, we can see that this is 1.695 seconds, and the y direction is 1.54 seconds. Along with this, we could also find the spring constant in each direction by using the equation from the video earlier, which is 4 pi squared times mass over time squared. From this, we can see that in the x direction it is 5.52 6.24 newtons per meter, and in the y direction is 6.691 newtons per meter. Thank you.